that where the information can be formulated in terms of a sequence of discrete symbols. Okay, so human language, computer code, mathematics, these are sequences of discrete symbols. You can also include in this DNA, proteins, and other things. There are things that are very difficult to reduce to a sequence of discrete symbols. So for example, the state of this room, we don't know how to reduce this to a string of, usefully at least, to a stream of discrete symbols. Which is why current AI systems work really well with language, but not so well, dealing with the real world. There are sort of, things that we can bolt on top of an LLM that allow them to interpret the content of the image. Not so much video yet, but it's very primitive in many ways. So how do we get AI systems to deal with the real world? The good news is that we have some ideas, okay, and systems that kind of are starting to work. The bad news is that we cannot use the type of generative architectures that have been so successful in the context of language. And I'll tell you very quickly, I don't want to be too technical, but I'll tell you why. If you give an AI system, a computer, if you give a system a sequence of symbols, let's say a bunch of words, right, a piece of text, and you train it to predict the next word that comes after, you cannot exactly predict which word will follow the sequence of words. But what you can train a machine learning system to do is predict basically what amounts to a probability distribution over all possible words in your dictionary. So every word in the dictionary now comes with a number that indicates with what probability every word will follow that sequence of words you just observed. Now what you can do is pick one word from this distribution, insert it into the input, and now it becomes part of the input, and you can predict the second word. Shift that into the input, predict the third word. This is called autoregressive prediction, and that's what LLMs are based on. Works really well for discrete symbols. If you try to apply this to video, so basically show a chunk of video, a few frames to a system or a few seconds, and ask it to predict what's going to happen next, this model does not work at all. I mean, it kind of works, but not well. And the reason is, you can't train a system to predict every detail in a video, and you can't even train it to produce a probability distribution over all possible futures of a video because there's an infinite number of them, and it's a mathematically intractable problem. If I take a video of this room, and I start from this side, and I turn the camera slowly, and I stop here, and I ask the system, predict what's going to happen next in the video. The system will probably predict that the camera is going to keep turning. There's no way it can predict what all of you look like. It's just, the information is just not there, it's impossible. When you train a system to make this kind of prediction, you basically kill it. It really doesn't work. So you have to use, but what you can tell at an abstract level is that there are people, sitting in seats, and I can't tell what they look like, but there's some, diversity of origins and gender and everything. So what you can do is build a system that finds this abstract representation, description of the world. It's not in terms of language, so that you can make those predictions. Okay. This architecture is called JEPA, Joint Embedding Predictive Architecture, and it would be a replacement for the GPT architecture, the GPT of ChatGPT, right? Which is generative. So those are non-generative architecture. I apologize for if I was too technical, but basically it's a new breed of AI system completely. Now, based on those architectures, you can also build world models. World models are quickly becoming a buzzword in the AI research, not so much in industry yet, but that will come. And what is a world model? It's a system that would allow an AI system to plan a sequence of actions to accomplish a task. So given the state of the world that you currently observe, and given an action that you imagine taking, the world model will predict the state of the world that would result from taking this action. If an AI system has such a world model, it can imagine what the effect of a sequence of action would be on the world. And if it's asked to accomplish a particular task, it can search for a sequence of actions that will accomplish this task. I call this objective-driven AI. So this is the kind of stuff that we're building in my new company. And I think it's a new generation of AI systems. And we'll see in a few months, a few years, whether this works out. Most of the applications are in industry. You can use this technique to build phenomenological models of complex behavior, a complex system, like say a power plant, a chemical plant, a steel mill, a jet engine, or a human cell, or a patient. If you had a complete model, physiological model of a patient, we could plan a sequence of treatments that would bring the patient to a good outcome, for example. So I think there's tons of applications of this in industry, which we hope to develop over the next year. And you know, this is a revolution that has not happened yet.